today I wanted to continue the study of fundamental solution. Of the Laplace equation. So we introduced the function u of x equals logarithm module x if n equal 2, module x to the power 2 minus n, and more or equal than 3. Here x equal x1, xn is a point in Rn. And correspondingly I introduced the function u epsilon of x equals integral u of y phi epsilon of x minus y dy. So it is a modified function u of x, and I proved the following thing, that u epsilon of x is equal to u of x for module x more than epsilon. This is one thing. And Laplacian of u epsilon equals 0 for module epsilon module x more than epsilon. And correspondingly Laplacian u equals 0 for x different from 0. Outside of the origin, the function u is a harmonic function, and the function u epsilon is harmonic outside the epsilon neighborhood. So this is this epsilon neighborhood. It's a ball of radius epsilon around 0. So here delta u epsilon equals 0, and u epsilon equal u outside this ball of radius epsilon. Now I wonder what can be said about Laplacian of a function u epsilon. Yeah. In fact, I want to prove that u is what is called fundamental solution, but first I have to define what it is, and to this end I wanted to find the following thing. U epsilon, Laplacian u epsilon is 0 outside, but here it can be not 0. So I'm interested in integral of Laplacian u epsilon. Now, where can we take this integral? Laplacian u epsilon of x dx. Integral we can take over the whole space, because here anyway Laplacian is 0. No, it is better to take it inside the ball of radius r. Yeah. So integral over ball of radius r. You have Laplacian u epsilon x dx. So dr is the set of x such that module x less or equal than r. Now, I wanted to remind the great equality, which is called Green's identity. Green's identity reads as follows. Suppose we have a domain, any domain D in the space Rn, and at every boundary point we have its unit external normal. Yes? No, depending on x, of course. So at every point of the boundary we have an external normal. And suppose we have two functions, f of x and g of x, in say C2 in D. In the whole D, in the closure of D means that it is twice differentiable up to the boundary, even at the boundary points. Then the identity is the following. Integral over D, the boundary is called S. F of x Laplacian g of x minus Laplacian f of x g of x dx equals integral along S f of x times gradient g of x dot n of x minus gradient f of x dot n of x times g of x, integral of all this ds. So this is the general Green's identity. For any two functions we have this. In fact, it is a result of integration by parts. I explained it in a separate lecture, so I just take this result. Now, in particular, integral over d, gradient u, Laplacian u, dx. No, for any function u, what it is, equals integral over d one dot Laplacian u minus Laplacian of 1 dot u dx. So let's take f equals u and f equals 1, g equals u. Take any function. So one of the function is 1. Equals integral over S over the surface. What is here? Gradient u dot n times 1 no, 1 is here, minus gradient of 1 times n times u ds. But 1 is a constant, so its gradient is 0. So remains only this, equals integral over s, gradient u dot n ds. This is the only thing. So we integral of Laplacian u over any domain d equals integral over the boundary of gradient u dot n ds. This is especially favorable in this case because we have a ball, we have a radial function, u is a radial, u epsilon is a radial function. So now let us perform these calculations. Now let's start from n equal 2. In this case, the sphere is just a circle of radius r. U epsilon of x equals u of x for module x more than epsilon. So we do it not for u epsilon but for u. So integral over br Laplacian u dx equals integral over s gradient equal integral u epsilon equals integral over s gradient u epsilon dot n ds on one hand. On the other hand, u epsilon is equal to u on the circle of radius r. No, we assume that r is more than epsilon. Yes, so we have this picture. This is epsilon, and this is r, like this. And so we consider it is SR. Consider integral over SR equals integral over S gradient U dot N ds. Now in this case ds is the dl. We integrate along the circle. Now what is u? U of x equals logarithm module x equals logarithm square root x1 square plus x2 square equals 1/2 logarithm x1 square plus x2 square. Du dxi equals 1 2 x1 square plus x2 square divided by 2xi equals xi divided by x1 square plus x2 square equals xi divided by model x square. So the square of the distance from the origin. And so gradient u is a vector x1, x2 divided by model x square equals x divided by model x square. Now, what is the unit vector? N. It is x. So it is vector collinear with x. So it is n of x equals x, vector x. No, its length should be 1 divided by model x. And so gradient u dot n at the point x equals x dot x divided by model x 2 and 1 cube. It is 1 over model x. Now, in particular, on SR, model x equals r, and gradient u dot n equals 1 over r, and integral over s gradient u dot n ds. No, it is equals 1 over r times the length of the circle is 2 pi r equals 2 pi. Yes? So this means, if you return to beginning, that integral over our ball Br delta u epsilon dx equals 2 pi. Okay, now let us move to it was done for n equal 2. So let me keep here only the result. Pi. Now we have n more equal than 3. Again, we find integral over Br, ball of radius r with center at 0, Laplacian u epsilon dx equals integral over SR. SR is the sphere of radius r. It is BR. It is SR. Gradient u epsilon dot n ds, which is equal integral over SR, gradient u dot n ds. because this is true for any dimension, for any n. So we have this, and now we have only to find gradient of u. U of x equals module x 2 minus n equals x1 square plus xn square to the power 2 minus n divided by 2 equals x1 square plus xn square to the power 1 minus n divided by 2. Now, gradient du dxi equals 1 minus n divided by 2 x1 square plus xn square to the power, we have to take 1 less minus n divided by 2 times 2xi equals, no 2 goes here, 2 minus n xi x1 square plus and so on plus x2 square minus n over 2 equals 2 minus n xi times module x to the power minus n, because what is written in the brackets is module x square. So gradient u equals, we have to take, it is one component of gradient. If you take all components of gradient, we have the form 2 minus n, gradient u at the point x. 2 minus n, x, no, this time vector x, module x minus n. Now, n normal vector to the sphere, unit normal vector external to the sphere of x equals x divided by module x. Yes? And so integral over SR gradient u dot n ds equals integral along SR gradient u 2 minus n x, let me module x minus n x dot x divided by module x ds equals, so what is here? Integral SR 2 minus n. Here x dot x is module x square, so it is module x to the power minus n plus 2 minus 1 ds equals 2 minus n. So this is module x equals r, so it is constant on the sphere, yes? So we have to write 2 minus n. Modulo x is r to the power 1 minus n, it is this, times area of SR. No, n minus 1 dimensional area of the sphere SR. So now what is the area of SR? Area of n-dimensional sphere. No, in fact we are most interesting in 2D. We already know the answer. In 3D we know, so in case n equals 3, area of SR equals 4 pi r squared. Yeah, and n equals 3, and integral of over SR gradient u dot n ds equals 2 minus n equals 3, so minus 1 r to the power minus 2 times 4p r square equals minus 4p. Minus 4 pi. So why there minus plus and here minus? No? Okay, it is a fact of the life. And now, so let me write here. N equals 3. This equal minus 4 pi. Now, in general, we have the following. There is a general formula for the volume of n-dimensional ball of radius r and of the surface of the sphere. So let alpha n is the volume of the ball B1 in Rn. B1 is the ball of radius 1. Volume of the ball Br. Then volume of Br equals alpha n r to the power n. It is easy to see. No, or you have to prove it. So the volume of any ball in n-dimensional sphere is proportional to nth power of its radius. Now, area of SR equals d dr volume of Br. Yes. So why? If you take this ball of radius r, this ball of radius r plus dr, this is dr, yes, this is r, yes. So the increment of volume when r goes to r plus dr is equal to, on one hand, this derivative, on the other hand, the area times the thickness of this. Look at this like a sort of watermelon, and this is its shell. So dr volume of Br, it is n alpha n r to the power n minus 1. So we have all a general formula, and so we see that integral or Br Laplacian u epsilon dx equals n alpha n r n minus 1, it is area of SR, times 2 minus n r 1 minus n. It is equal to minus n minus 2, yes, alpha n. Our goals. That's it. This is what was our goal. And this is the hint how can you normalize this function. U epsilon u was temporary notation. So let me introduce this definition. Phi epsilon phi of x equals minus 1 over 2 pi logarithm module x if n equal 2. And 1 over n minus 2 alpha n module x 2 minus n if n more or equal than 3. Now you can see that for case n equal 3 this agrees with this minus 4 pi. So why minus here and why all this? So and phi epsilon x equals integral phi of y phi small epsilon of x minus y dy. So it is modified, and phi epsilon of x is equal to phi of x for module x more than epsilon, more or equally. That's it. And because we changed sign here, we have the following thing. And here we did not need to. Here we also changed sign. Instead of 2 minus n, we write n minus 2. We have the following thing, that integral over Br delta phi epsilon dx equals minus 1. But following some other reasons, it is better to change sign not here, but change sign in delta. So we are solving the equation. We substitute we change signs here. So integral over BR minus delta phi epsilon dx equals 1. So it is one thing. Other thing about this phi epsilon is that minus delta phi epsilon of x is identically 0 for model x more than epsilon. Yes? We can add here other properties. Minus delta phi epsilon more equal than 0 for all x. No, I don't prove it. In fact, it is not so necessary. Minus delta phi epsilon depends only on model x. No, the last is because both phi is radial function, depends only on radius, and phi small epsilon, the modifier depends only on radius. So as a result, this function also depends only on the radius. So the function minus delta phi epsilon has the properties of a function which is converging to delta function. It looks like delta-like function. No, if it is 0, then we see that this function is concentrated near 0 in the epsilon neighborhood. Its integral is 1, it is positive, so it is just like delta function. And so we can assume that minus delta, if epsilon tends to 0, the function phi epsilon goes to 0, goes to phi everywhere. It becomes phi when epsilon becomes small enough. And so we can assume that minus delta phi without epsilon equals simply delta function of x. It is unit mass concentrated at 0. That's it. And now I wanted to proceed to one next important thing. So let me introduce one more name here. Equation minus delta u equals 0 for harmonic function is called Laplace equation. And equation minus delta u equals f of x, where f is a given function, is called Poissons equation. So Poisson's equation is not less important than Laplace equation. It is indispensable in the study of Laplace equation. and we'll use it. And so our function phi, which is written here, is a solution of the following equation. Consider the equation minus delta u of x equals delta function of x. If you remember, I told that delta function is the simplest function which exists. Yes, we cannot find a function simpler than delta function. It's most elementary function, delta of x, and if you solve this equation, solution is from here. You see minus delta of function phi is delta of x. So u of x equals phi of x. Phi, which is given by these formulas. And therefore, phi of x is called fundamental solution of the Poisson equation. So this is what I mentioned from the very beginning, that the fundamental solution is really fundamental because it solves with the most elementary function. And now if you know how to solve this equation for one delta function, we can also multiply this function. So suppose f of x equals sum c k delta of x minus xk, x minus ak. Yes, k, say from 1 to some n. So we take several delta functions with the corresponding weights. And then for each of these functions, solution is also the fundamental solution shifted by the vector ak, so that its singularity is at the point ak, and multiplied by coefficient ck. So then for each of them we have solution, and because the equation is linear, the sum of function produces in the left hand side produces sum of right hand sides, and multiplication of u by constant results in multiplication by result by constant. You have a solution u of x equals sum ck phi of x minus ak, k from 1 to n. Yes. So this way we can solve equation with many delta functions in the right hand side. But we can consider not only the finite sets of delta functions, but the families of delta functions, which are parameterized by some point, say, a in space. So consider the function delta of f of x. Instead of sum, I write integral, say, phi of y delta of x minus y instead of a, dy. So the same delta functions are somehow dispersed in some domain. So integral, no, suppose that y is in some domain D. No, we can consider, of course, the whole space, but then we have to impose some conditions on C, say, of integrability and so on. Let's consider first bounded domain U. Then for each of these 4 points y, we have we have this point x. The point y is x is fixed, y is changing in some domain D. Yes. Then for each of this domain y, we have this coefficient c of y, and it produces some solution phi of x minus y multiplied by c of y. So for any point y in this domain, we have this solution, and then we have to add them with this weight c of y. But if you have such continuous system of points, then instead of addition, we have integration. And this means that u minus delta u equals f. F is this. So u of x equals integral over y in D, c of y, delta of x minus y, dy. Yes? But now let's look once again what is integral c of y delta of x minus y. We had the formula f of x equals integral f of y delta x minus y dy. Yes? And now it is f of x. And here f of x is integral c of y delta. No, this means that instead of c we have to write f. Yes? And then for each point y we have this solution, fundamental solution, and hence we can write solution for our equation. U of x equals integral f of y phi of x minus y dy. Now let me propose some I would say mechanical, or I would say hydrodynamical interpretation of this formula. Suppose that we have, as I gave this example, a horizontal layer of porous medium, say of sand. Yeah? In this porous medium, the pressure P of x, it is pressure, satisfies equation Laplacian P equal 0. If there is nothing is done with it, say all the fluid is moving inside this layer. But things change when you, say, drill a well and start, say, injecting water or fluid which is here, say water, inside this layer. Yes? Inside this reservoir, or oil people call such things reservoir, or oil or water people. Then if you look from above, we have this piece of reservoir, we have a piece of this layer. I assume that layer is thin, so all the motions are horizontal. And here is the well, and fluid is moving out of the well. Yeah? And what is the pressure, how it behaves? Pressure is 0 outside of this point, but nonetheless integral of gradient of this pressure of the flux, so it is say contour S, integral over S, say V dot N ds equals Q. It is productivity of this injecting well. Yes? It is N. It is not 0. And so we have the equation minus delta P equals, it is the point, say, x0, equals delta of x minus x0 times Q. Yes? So each source of water gives you this delta-like term in the right-hand side. If you have here a production well such that it pumps water outside of this reservoir, then Q becomes negative. Yes? So in this case, one well gives you some flow, and what is this flow? Because this flow is incompressible, its velocity is inversely proportional to the distance. Yes? And so the pressure behaves like logarithm, so it increases to infinity as we approach the well, this point x0. So we have this source. If you have different source or sink, say it is this is called source, and this is called sink. If you have this sink, then you have a fluid moving to this point. The pressure behaves like a solution of this equation with Q negative. And if you have both source and sink, the pressure and the flow will be a sum of this partial terms due to just one source alone and sink alone. Now, if you have some number of sources and sinks throughout this layer, then you have the pressure is sum of the pressures produced by each well. And we can imagine that these wells are continuously dispersed all over the this reservoir. No, this happens if the number of the wells is measured in thousands, like in a big oil field. Then we can approximately write this like integral. And so we have a density of sources, which can be positive or negative. And so if you have g of x density of sources, then p of x equals integral g of x phi g of y of x minus y dy. So here we measure at point x, the source is at the point y. This source produces this field of pressure, and the total pressure at the point Px is produced by the integral of results of all these sources separately. Yes. Therefore, fundamental solution is sometimes called the source function. Yes. Now, to be more concrete, let us solve one problem. Some examples. Have a good time. Bye.